from days to seconds. Is it really that fast? And can we trust it? And is this the end of the CFD careers as we know them? Today we are bringing geometric deep learning to Simcenter STAR-CCM+. My name is Rodolfo Piccioli, and together with me in the London Hammersmith studios is Monsieur Cédric Tachot from the product management team, who will help us separate the hype from reality. Cédric, bonjour, welcome to the London Hammersmith studios.
Thank you, buongiorno, Rodolfo.
Buongiorno.
That's my full capability in Italian, sorry, but I did my best. Happy to be here.
Let's stick to English then, yes. Yeah. So, geometric deep learning. First and most important question, how do we do it in Simcenter STAR-CCM+?
So let me set the ground and explain a little bit what we are talking about. We are talking about here using AI to predict results extremely quickly. As you said, in seconds or minutes, depending on what you want to do your prediction on. So if it's scalar values or scalar fields. Our idea was to provide a smooth workflow that is contained inside a CFD tool, STAR-CCM+ in our case, and have all the workflow to do those AI steps from building the training dataset to the inferences in one single and familiar environment with a smooth workflow. So that's what we did.
So results, you said in seconds or minutes, but can we trust them?
That's one of the big questions. How much trust can I put in AI to know how predictive a model, a registered model using AI can be? It's like any other registered model. So we need, at some point, to check on unseen designs and compare what is the prediction, what is the real result. How much am I different? And I need, and we're providing tool to quantify that. So how much with R² or any classical error metrics that we have, how much, and am I capturing the trends? Because when I'm using an AI registered model, I need also to be sure that when the drag is decreasing for some reason, if I'm having the same sequence of design, whether I'm using AI or CFD, I should have and I must have the same trends. So we're also providing tools to check that accuracy. And with that accuracy check, I know how much I can trust my model.
Right. So if we go back 20 years ago, which is roughly when we started doing CFD, without mentioning the age, people were not trusting CFD at the time, and it was always necessary to have experimental measurements to keep CFD grounded. And nowadays, actually, CFD for many applications is considered the ground truth. So what is, in 2026, the relationship between AI and CFD?
I think the parallel you're doing is really valid. So today, with this feature, we are capable of starting to predict results really quickly. So the question is how much, again, trust related to the previous question I can put inside it, and how can I make my engineering decisions? Because at the end of the day, that's what matters. I mean, we are doing simulations to provide answers and to make engineering decisions. So those decisions can be AI-driven. Now the thing is to validate and to make my final decision. Today, in 2026, I will need CFD to validate my AI result. Today, that's the way it is. I don't know about tomorrow. I don't know about what will happen in the upcoming years and what will be the next technology step or leap. I don't know, but today, I think this parallel you made is really valid. We can see CFD today as experiment was seen 20 years ago, and AI today as CFD was seen 20 years ago.
Right, and you mentioned different types of predictions like scalars and surfaces and volumes. What is the difference between them in terms of accuracy and computational time?
Yeah. So In terms of definition, a scalar value, a quantity, is basically a report from STAR-CCM plus, scalar fields, field functions, whether it's in volume or surfaces.
So if we stick to a, let's consider an example of external aerodynamics, scalar value would be something like the drag coefficient, lift coefficient, and surfaces and volumes would be the pressure field, the velocity field, the turbulence fields, either on surfaces like plane sections or the entire volume.
Yeah, correct. That's it. So based on that information that we have, we do our training. So we specify during the training what we're interested in. We won't train an AI model on everything. We'll train it on purpose to answer our engineering questions that we will have in the future. I'm doing behind the scene kind of two trainings. One for the scalar values, engineering quantities that I'm interested in, and one other for the fields. First one is faster to obtain. The second one helps me as an engineer to understand the behavior. It depends on what is your objective. So both solutions are valid. I mean, you have workflows where you want to leverage AI to drive an optimization study faster. So you can leverage AI and your registered model to run an optimization study. In that case, you need only a scalar quantity, a scalar value. So the direct KPI prediction is perfect for that. Now, when you find something interesting or really bad, if that's correct, you can look at your fields again to understand better. So there is no one-fits-for-all answer in your question. It really depends on what is your problem, what is the engineering question you want to answer. Fact is, KPI predictions are faster in terms of training and inferences. Scalar trainings, scalar field trainings are slower, inferences are slower, but they are providing extra information.
Right, and very, very exciting. Shall we have a quick look at how this works?
Sure.
So let's connect to Toby, and yeah, he's here. Hello, Toby. How are you today?
Hi, Toby.
Hi, Rodolfo. Hi, Cédric. All good here, thank you.
Good, good. All right. We are doing very well as well here. And right, do you want to say a few words about yourself, please?
Yeah, thank you very much. So I'm an application engineer working in the global support team, and I have a specialization in AI for simulation. So geometric deep learning is basically my specialization.
Okay, so right person at the right time here. Please go ahead to tell us something about geometric deep learning then.
Yeah, so today I'm going to show you a little bit about what geometric deep learning is going to look like inside STAR-CCM+. And we're going to start here in Design Manager, where we need to generate some data. So in Design Manager, it's perfect for generating data. You can provide a base sim file, and then the field functions, KPIs, scenes, and reports that you would like from your sim file. Based on this, you can run a study, and then you'll be able to visualize it with your design table and your scenes all in Design Manager.
Yes, if I have already some data because I ran, let's say, a DOE study in the past, can I reuse those?
Yes. We now have a functionality in Design Manager where you can import sim files from a previous DOE, which will save you some time in running all the CFD, and you can use those as well.
Thank you, please.
Yeah, so the next step, once you've run your DOE or you've imported it, is to make an AI ROM dataset. And essentially, you just need to fill out the KPIs that you want to learn, and Design Manager will then fill in the field functions required for all of those KPIs. This is then saved in Design Manager, and you're free to start AI ROM training. So the first step in AI ROM training is you need to select your dataset from the saved datasets you have in Design Manager that you've just made. And then you need to choose your hyperparameters. So the most important hyperparameters that we have are going to be the number of epochs, how long you train for, the max learning rate, determining your step size, and also things like the number of points that you choose to pass to the model.
Okay, so to say something more to the CFD engineers, who are probably most of the attendees today, the epochs correspond more or less to the iterations in a CFD simulation. And the number of points, so we are not doing the training over the entire mesh, which can be hundreds of millions or even billions of points, but in order to save memory, we are basically doing the training over a reduced number of points. Is this right?
Yeah, absolutely. So on your first point, an epoch and an iteration are very similar. Not quite the same, but very similar. And yeah, absolutely. A CFD mesh, as you mentioned, has millions of points, and we can't fit all of those points and all that data on the GPU. So to save space and memory and time in training, we're going to take a subsample of all of those points and pass just that for each design to the GPU.
Okay, thank you. Please go ahead.
Yeah, so once you've chosen your data set and you've decided on your number of points, you're then free to choose from the default options small, medium and large, which will dictate the size of your model architecture. From there, you just need to select the GPU devices that you have available and you're free to train. So this might take a while, but here's an example of one that has already finished, and you can see now that we have a loss function plot. So the blue line here represents the training loss, and the red line slightly above it represents the validation loss. And these are our two training data sets that we used in training. You can see for our two models here, the field model and the zero-D KPI model, we have slightly different graphs, but both of them have trained pretty well. Okay, so once you've analyzed your loss plots and you're happy with the convergence of your training loss and your validation loss, you can also view the metadata of your model in the summary section. In the summary section, you have the inputs into your model, which includes your data, the KPIs, and the field functions. You also have the hyperparameters of your model architecture, the location of the models on your disk drive, and as well the validation sets. This allows you to compare metadata between models and make sure you don't copy any in future iterations. So once you're happy with your model, the next step is to validate it with a test study. The whole point of a test study is to infer on the geometries you set aside. Your model hasn't previously seen these, but you can set up a test study and infer on your zero-D KPI and your field model. So this will come in through Design Manager, and you'll be able to see your design table with the predicted KPIs, and you'll also be able to visualize your fields in a scene. So it's all well and good being able to do a test study within Design Manager, but you may also want to infer your model on an STL that you get from somewhere else. So we have the functionality to do this, and you'll be able to provide external STLs and get a rapid inference of a zero-D KPI. So something like drag coefficient. You can do this through a response study, and you'll be able to provide any STL that you like from any dataset. Yeah, so that's pretty much it for geometric deep learning in Design Manager at the moment. I'm looking forward to you guys testing it out. I've been having lots of fun with it so far, so I hope it's useful to you guys as well.
Yeah, looks amazing, and I definitely look forward to using it as well. Thank you very much, Toby, for being here with us today.
Thank you, Rodolfo. Thank you, Cédric.
Cédric, back to you. Can we use geometric deep learning in Simcenter STAR-CCM Plus for both analyze geometric changes but also boundary conditions? Let's stick to the external aerodynamic example. If I want to see how the drag changes when I change the inlet velocity, can I do it?
Yeah, obviously you can do it. So, in a nutshell, you've understood it by seeing it, but and maybe because of your knowledge, this AI runs doesn't need to rely on geometrical parameterization. So obviously we are taking into consideration changes in terms of boundary condition and all of that. So here now in 2026, you can apply a different value for your boundary condition to be a second velocity inlet, and you can use your register in the model to try a set of values between the values you had set in your training dataset. AI is done for that. So you can or stick to a velocity that you are interested in and you train on, but you can also go between the ranges and start to do your interpolation. AI is made for that.
$1 million question. How many data do I need in order to get reliable results?
Yeah, so you'll save your million. I don't have an answer that fits for all. What I can do is providing you some examples. So, for example, on the aero SUV dataset, that is something you know from Siemens for years, to start to be predictive in a given location of the design space, only 40 designs were required. By chance, we are using aero SUV dataset a lot, so we already had some of them. So this was not a cost, we already had them. So we had to compute additional results to do our training. But with 40 designs, we start to be predictive in the area of the design space we're looking at. So what we are seeing and what is the trend today in 2026 on the market, we selected a transformer neural network approach because it requires less designs to start to be predictive. And again, 40 designs to do external aerodynamics, it's not a lot. It's really not a lot. If you compare to previous AI technologies, 40 is really, really good. So yeah, transformer allows you to use less designs to start to be predictive.
Okay, so really thinking loud now. Let's say that we run the training, I have the AI model. Can I use AI for an optimization study?
Yeah, obviously you can. Actually, in the design manager process, you can see registered modeling as being another way of evaluating a result. Or you can do CFD, or you can use another evaluation method. And actually, we already had it with surrogate models. That being said, you can do whatever study you want, including optimization, changing the evaluation method to registered models, whether they're from AI or not, but you can do it, and drive your optimization study. So your AI registered model will fit in your process, and instead of calculating using CFD, you will predict your Scalar values really quickly, and your optimization algorithm, in our case Sherpa, will drive it and will do your optimization for you. So you just have to say, what is my budget? When we're talking about AI, I can do thousands of simulations. We're talking about seconds. And I can run my optimization for 5,000 designs, and I will get an optimal solution according to the parameters I set for my optimization.
Good. In my introduction, I asked the provocative question if this is the end of the CFD careers as we know them. I guess this is a tough question to answer. Let's try to simplify it a little bit. What are the user personas we are targeting with the geometric deep learning in Simcenter STAR-CCM+?
Okay, so user persona, you have two different things. Training the registered model is one bit of it. The other one is using that registered model to do predictions or inferences. So for the first part, which is doing the training, here you need to understand what is CFD. So you need to be a CFD engineer, because you, as a CFD engineer, you know what is your design space, you know which design you need, and which design you already have to start the training. So CFD engineer. But if you want to go beyond, and while you're training, you want to adapt, fine-tune your hyperparameters, we're providing tools that are suitable for CFD engineers, but you can also be an AI expert where you want to fine-tune things with the same training data set, you want to have a better accuracy and all of that. So that's the two main user persona we are having for the training part. Now, when it comes to inference, so intuition, and today we are releasing something in STAR-CCM Plus Design Manager and STAR-CCM Plus later. Obviously, CFD engineers can do inferences. They are in Design Manager or in STAR-CCM Plus, they click a button, they get the results. Obvious. Now, what will come next? It depends on what you're doing. If you're taking again this example of external aero, maybe I want to design a car. I want it to be nice and efficient. How do I do that? Nice, Usually I have stylists that are doing that. After they have an idea, they give it to a CAD team that are creating a geometry out of it. What if those people could have tools when they are creating the geometry that tells us, okay, what you modified here will impact the drag, will increase the drag, or will lower the drag. Even if they are not CFD engineers, they are interested in that. So we want to go that route. And even earlier for the stylist himself, when he is playing with clay, or depending on how they are doing it, they could have insights already based on the shape they are having, what impact it will have on the drag using an AI registered model. So that's definitely user persona we are targeting in the future. So first, CFD engineers, CFD users, but it goes beyond that, depending on your engineering problem.
Right, and I think the quote that CFD engineers will not be replaced by AI, but CFD engineers who don't use AI will be replaced by those who use it might be true also in this case.
Probably.
Yeah, and some more technical questions. Hardware.
Yeah. Hardware, you have some keywords here already. AI. In my mind, I hear AI, GPU. So obviously, to do an AI training, yeah, I said obviously, but it's not always obvious, but we are leveraging GPUs because they are faster for those calculations. So an AI training is definitely faster on GPU, and it doesn't worth it to do it on CPUs. We tried, it's crazy slow. So on GPUs for training. For inference, the question is raised again because it could worth it. An inference is crazy fast. We are talking about seconds for scalar values. Fact is, it's 10 times faster using GPUs than CPUs. So we are providing a framework that works only with GPUs. And as a release time, when I'm talking right now, it's only NVIDIA GPUs, but it will be expanded to other GPUs soon.
Are there applications that we know work better than others?
I can tell you that we tested it heavily on external error. We know it works. We tested it quickly on other applications. It works. So today I'm saying, and I'm giving a lot of examples around external error because we intensively tested it. But this technology is not restricted to one given physics. I mean, it's not even restricted to CFD. You can use the same technology on FEA, on Crash, on whatever.
Excellent. And last question, licensing.
Yeah, licensing. So this is a new capability. It involves new possibilities and it creates new added value. So as you can expect, there is an additional license attached to it. So only one license to do both and training and inference. So with that additional license, you do your training. When you're finished with your training, you do as many inferences as you need. And actually, an inference, you understood it crazy fast. So the license is going to be taken for a couple of seconds when doing an inference. But yeah, only one license to do both.
Cédric, it was a pleasure to have you here today. Thank you very much.
Yeah, it was a pleasure for me. I took my French again. Excuse my French. I know it means something else. Anyway, yeah, it was a pleasure for me to be here in London with you and to be in London and to be with you. Thank you very much.
And thank you very much especially for you to attend from home, from your office or home office, and I hope to see you soon. Right, so if we go back 20 years ago, which is roughly when we started doing CFD without mentioning the age.
I was graduated last year. I don't know what you're talking about.